So wavelet transform section, I think we covered in the last class where we looked at how wavelet transform can be used to analyze the non-stationary signals, and in there we are using a certain basis function. That basis function is a small part of wavelet we call. That wavelet we can define using this mathematical equation. This wavelet we can denote a certain, basis function or a small function that we can use to compare with the original signal, and this basis function can be adjusted as we want by changing the values of a and b. So a value and b value correspond to scaling and also shifting. So, and then those are the parameters that define this basis function of the wavelet transform. So using these basis functions, we can combine multiple basis functions appropriately, and then we can generate the original signal. So that is regarding wavelet transforms. And there are different various wavelet basis functions that we can use to compare the original signal with. And these are some of the shapes of the wavelet basis functions. So that is a brief, I think, introduction to wavelet transforms. So if you prefer, if you can search more about the wavelet transform in a free time, also understand like how you can actually implement it on certain images, and how you can increase the quality of certain images using this transform method. In the last class, we looked at some simulations in MATLAB where we compared, where we did some, wavelet transforms, and we used wavelet transform to filter out certain image into a grayscale image, and then afterwards we did the same thing to an image using Fourier transform, and then we discussed how those contrast is different, how the filtered out signals are different in Fourier transform method and the wavelet method. And we discussed like the advantages of wavelet transform, especially in cases where we have some images which have like contrast areas, where it has a lot of contrast in certain areas of the image. So those things we discussed in the last class. So in today's class, we'll be going through the section on adaptive FIR filters, or basically adaptive filters. So we will be generally talking about these adaptive filters. So the word adaptive is used to denote that the coefficients of the filter is going to adaptively change with the time. So the reason for changing the coefficients is that based on the application that we use this filter for, we need to make the desired signal equal to the output of the filter. So we will discuss about those terms like desired signal, output signal, and then input signal, filter coefficients, error signal. Those things we can discuss separately. So by changing the values of the filter coefficients, we can change the output of the filter such that the desired signal that we want to take from the filter is almost equal to the output signal from the from the filter. So the output signal from the filter we denote using yn, and we are trying to make dn and yn almost equal. So we define something called the error signal, which is defined using en. that en should be made as small as possible. So the en is changed by changing the values of the filter coefficients, and we have certain algorithm to change the filter coefficients. So one algorithm is this method of minimizing the error using least mean square method. So we are using some method called least mean square method, and using that we are going to change the values of the FIR filter coefficients. So the main goal is to minimize the error, and if we draw the function of error with respect to the filter coefficients, we can get a point in the function where the slope of the function is equal to 0. The slope we call as the gradient is the value we are checking in here in this function, and if it becomes 0, that means that the function will have a certain minimum or a maximum. So in here we are actually considering the mean square method. So the least mean square method, uh, we are considering the square value of the error. So error values, square amount we are taking, and we are considering that. So we are considering that as the function in here. So it's most of the time it's going to be something positive. It's not having any negative values. It's a square value. So error square value is always a positive value. And we are trying to find these places where the gradient becomes 0, right? And there could be some maximum places also where the gradient becomes 0. So in order to find out exactly where the error becomes minimum, we need to also find the second derivative of the function. So the second derivative of the function we will find, and that also should be um, uh, fulfilling a certain criteria, which is that that value should be positive. So we will discuss also about that. If you have heard about Hessian value of a function, that Hessian value of that function is what we are talking about as the second derivative of the function. So the second derivative of this function that we are considering should be positive. And if that is positive, that means that the point we are considering has a minimum, or there is a minimum occurring in that position in the function. So what is the importance of this finding the minimum, right? The finding the minimum is that we want to minimize the error. We want to minimize whatever the error that we have observed in this filter. So finding the minimum value of the function is important for us to find the corresponding filter coefficients for that. So the filter coefficient values must be generated such that the the error is minimized. So we need to find like the minimum the optimal filter coefficients, and we are going to find that optimal filter coefficients by incrementing the current filter coefficients by a delta value of the filter coefficient value. So we are going to make some small changes to the filter coefficient, and then we are going to check whether the final output of the filter coefficient that we get will be actually helping us to reduce the error or not. So that is, I think, what we discussed in the last class. So I will continue with that. Before going to that, also I want to share with you that in the LMS, I have provided you a lecture note and week under the week number under the week number 13, I have given this reference material, and you can go to that, and then you can refer some notes related to adaptive filters. I will be following this note, and I will be kind of going through kind of the most you know highlighting parts that are required for us to find the optimal filter coefficients, right? So this note gives you some, I mean, information regarding the introduction to matrices, linear algebra, and optimization, gradient and Hessian, and also how you can find the gradient, and how you can find the Hessian, and what Hessian means. Those things they are mentioned in here. Also, this mentions some things related to the stochastic processes. Stochastic processes means the random processes that we already, I think, discussed in the previous classes. So in the stochastic processes, we have discussed about mean, covariance, correlation, metrics, and those things also are mentioned in here in a mathematical manner. If you have any questions related to these, you just let me know. So I think we have discussed these parameters and also these functions. So I think the ones that we discussed are also similar to this. So if you see any any problems, you can let me know anytime, and you can just email me, or you can let me know in the class. So in this, so there's some introduction to the random processes. After that, we come into this adaptive filtering process and the related sections in there, where the adaptive filter and its process is explained. So this is what we are going to discuss, and after that we can actually go into the next sections related to stochastic models. So before going that, we will be discussing this part in this today's lecture. So if you have any questions, you let me know. So in these calculations, I have discussed some things so related to how you can find the delta value that you are adding to the field coefficients. So this is one method of doing uh, the calculation of optimal field coefficients. So the field coefficients optimal value we are trying to find such that uh, we we are we are able to reach this point where this function is minimized. So I mean, if we are currently in another position in this function, we are trying to come from that position into this minimum point. I think in the last point that we discussed, we have discussed about that. So the global minimum is something that we are trying to achieve uh, once we are designing this filter coefficients adaptively. So currently, initially, you can have a filter coefficient somewhere in this function, right, which is defined as the error function. And then, so in here, you can take that this is the error squared. This is this y-axis as error squared in here. So, and then you can consider that initially you start in here, then you want to go to the place where this error function is minimized. In order for you to go to that place, first you need to find the gradient of this function. So the gradient of this function you can find mathematically by taking the differentiation of this function with respect to the this coefficient h. So this, as you can see, this function is something that we have drawn with respect to this filter coefficient. So with respect to filter coefficients, we have drawn this function, right? So in here, we are uh, we are actually assuming that we know this distribution. We are assuming that we know how error is changing with respect to the filter coefficient. So by using this function, we can take this uh, gradient of this function, and then as the gradient becomes zero, or it reaches zero, we can say that gradient becomes, I mean, gradient comes closer to zero means that the error is going to reach a minimum value. So as I said, sometimes we cannot really say that uh, just because the gradient is zero, we cannot say that it is a minimum value. So you need to test using another test, which is finding the Hessian value, uh, about which we are going to discuss. But basically, Hessian means taking the second derivative of this function that we are considering. So, I mean, in gradient, we only take the first derivative. In the Hessian, we are taking derivative up to second time. So in that note also, you I think you will be able to see that that mentioned. So in Hessian, the definition of Hessian, you will be able to see in that PDF that I just mentioned, and you can refer the basic idea about Hessian in that PDF. So I will explain also in this lecture session. So in here, now if you want to find the minimum distance or the minimum amount of change that we want to make in the filter coefficients, we can we can find that value first by taking the derivative of this error value with respect to the filter coefficients. In here, you can see that not only error value, but I also have included something called the mu, and also 2 divided by 2. In here, we are going to take the mean value of the error. This method we call as the least mean squared error method. So because of that, we are going to take the mean value of the error. So in order to take the mean value, we are taking the average of that uh, error value. in order to take the average, we are dividing by 2, and then we are taking the mu, the error mean value of the error, and also we are multiplying with the mu value, which is a new constant we are adding here. So the mean value is actually the mu value. Mu value is actually something new, and it is called the learning rate of this uh, algorithm. Learning rate. So in here, this mu value is something we have to decide based on maybe some trial and error. The mu value is something we have to decide by giving some values, and then we decide what is the optimal value uh, by trial and error. So it is something that is not fixed, or we cannot sometimes calculate that theoretically. You need to decide that value for your system by doing some tests and deciding the best one. You can decide that by checking the error value that you get for each mu value that you input to this algorithm. So if the error value is changing very fast, fluctuating very fast, that means the mu value you are maybe including might not be the suitable one. The error value should change very step by step in incremented manner. So in order for us to capture all the possible error values, we need to define the mu value, such that the mu value is changing the error values in small steps. So this is regarding basically how we can determine this delta H value. That delta H value we can decide by taking the derivative of this error function with respect to the filter coefficients. So after you find the derivative, you can get the you can find the derivative, as I think I have done in here. So I think you can if I come in here, I can substitute for yn an equation which relates the which has components of the filter coefficients. So yn I can denote using h values or filter coefficients. So so in here, if I'm going to substitute yn can be substituted with hn convolution xn, and that also can be written as a summation of hm and xn minus m. So that we can include in here, which will have the filter coefficient values in here. So if we consider this entire thing and we differentiate that, we can differentiate the entire expression inside the brackets first. So we take the square term out, and then 2, and then dn minus this expression, which is this expression is yn. So we leave as it is. Then dn will be a constant, or it doesn't have any filter coefficient values, so it will be 0. So we will be differentiating this expression with respect to the certain filter coefficient hm. So if we have a certain filter coefficient in consideration at one point, we can consider that it as a constant. Then we can get the derivative as the xn minus 1 xn minus m. So basically this expression that we have in here inside the summation can be differentiated with respect to each filter coefficient once we do that, the value that is remaining will be xn minus m. So this is what you will get as the output of the differentiation. And then the total outcome will be looking like this, which will be something like this, where you have delta hm, delta value of the hm, which is the delta value where you are having the filter coefficients changed, is equal to the minus, because there's a minus sign that is remaining here in this above expression, this mu, where the learning rate is mu, and then en, which this dn minus yn equals to en, then xn minus m. So x means like the input signal, and this expression gives us how you can multiply the error signals and input signals to get the smallest increment required in the filter coefficients. So this is one method of increment, finding this optimal increment in the filter coefficients. So this can be used to find the optimal like filter coefficient values at a certain time instance, uh, and by using the previous filter coefficient values. So this kind of a iterative calculation uh, and a method can be used to update the values of filter coefficients. If you have a certain filter coefficient values at time n, then the value of filter coefficients at n plus 1 is going to be uh, this value, which is a combination of the current filter coefficient value and the increment that you have made in the filter coefficient values. So this depends on also the step size of the mu, and which is included in this delta value of hm. So mu also is uh, one parameter in this equation that helps us to increment the value of h. So that is, I think, what we have discussed. So we have discussed mainly about that filter where structure. So this is a place where we have some data samples that we have, and the data samples are getting, getting filtered through this filter. Then the filter coefficients are H0, H1, H2, and the certain samples of certain duration are multiplied with corresponding filter coefficients. And so the output is taken as yn. So that would be kind of the basic operation of a FIR filter, and we are going to discuss about the FIR filters itself as today as well. Today as well, we are going to talk about that filters and how we can update the filter coefficients. So in this session, so the mathematical modeling of all the kind of update, um, I mean, the mathematical way of updating the filter coefficients will be discussed again. So in here, I think we will discuss more about the least mean square method. So least mean square method we discussed in the last session also. In this session, we are going to add, mathematical definitions more to what we discussed, and kind of organize the mathematical models more. So as I told that we are going to be looking at a certain filter. It could be a FIR filter or IIR filter. It could be any filter, but if we consider FIR filter first, we are going to have that block diagram that I mentioned before, where we have a finite number of blocks, finite number of coefficients in the filter. This one we have defined as the FIR filter. So the FIR filter coefficients are H naught, H1, H2, and H3. This filter, of course, we have fixed filter coefficients. However, with the adaptive filters, we are going to update the filter coefficients in an adaptive manner, considering some aspects of the filter output and checking whether the filter output is reaching the desired output or not. So we are actually updating all these, filter coefficients using a certain algorithm. So the algorithm we are going to use basically is the least mean square method. We are going to use something called the least mean square method to update the filter coefficients. I will explain to you about the reason for using this method as well. So that is what we are going to discuss today. So why we use this specific method and what are the properties of the signals that we are considering as the input signal, output signal, error signal, and those things. So we are going to anyway update the filter coefficients using the least mean squares method. So when we consider this kind of filter, we are going to uh, update its filter coefficients such that the output is as close to as the desired signal that we expect from the filter. So sometimes the output is not as the one that we want, but we want to make it as close as possible to the desired signal. So instead of drawing all these filter coefficients, after this, I will be basically using the certain block to represent the filter without drawing the each and every component inside the filter. I will be also able to draw the filter using a box. This one I can use to denote the filter. So whatever the FIRO filter will have this coefficients which we denoted as HM, and whatever the input signal we denoted as XN, right? XN, HM. So once we get a certain output, it will be YN, and then that output we are going to compare with the DN or the desired signal. So either we can actually take the subtraction in a way that we are subtracting dn with yn. So we subtract and we find this error value. Based on that error value, we are going to compute the optimal weight values for the filter using a certain algorithm. You use certain algorithm. So in here we are going to use least mean squares algorithm, and we are going to find least mean squares method. We are going to find the optimal H naught values or optimal H values, filter coefficient, optimal values we are going to find using the LMS algorithm. So I will say H optimal. H optimal values I find, and then I just update the filter coefficients I already have. So that updating, I will denote by going through this. I can denote using this slanted arrow, and I can denote that I'm updating the filter coefficients. So the updated filter coefficients will be used for the next time of filtering, and the next time the filter output will be changed, and then again error will be calculated, and the error will be, if the error is higher than before, then whatever the algorithm that we use here will be updated such that the uh, filter coefficients are changed in the opposite direction, for example. So if the filter coefficients are updated using certain by updating using some delta value, adding a certain delta value, we are going to add that delta value by considering the possibility of reducing the error value in the uh, in the direction where the error magnitude is reducing. If the error magnitude is given in here in the y-axis, and the uh, if the error is increasing, the error is increasing means error goes in this manner. But if we want to go in the other direction, we can change the the direction of moving by changing the one thing we can do is we can change the mu value or the learning rate value, and then we can also consider the gradient value, and we will try to find the h or the filter coefficient values that will make the gradient go to 0. So the target is to make the gradient go to 0 while also make the Hessian go to positive value. Hessian means that we are considering the second derivative of the error function. So Hessian means we are taking the double derivative of the Hessian of the error function with respect to the filter coefficient. So we are going to take the error function. We are going to take the derivative, and in here we are taking the derivative for 2 times. If the derivative value is positive, we can directly say that the output of this second derivative is something positive. Then we can conclude that the point that we have found uh, uh, as the last point in this function is something that is um, having a minimum. That function at that point of consideration has a minimum. So if we go to a certain place where the gradient is 0, and then the Hessian value gradient should be almost 0, and Hessian value should be something that is above 0. That means it should be something positive. If these conditions are satisfied, we normally say that we are at a minimum in the function. So why we do all this is that we try to minimize the error. So we need to find this minimum point. So we can find the parameters such as gradient and Hessian, and then using those parameters we can find the optimal point in the error function that we need to operate in, such that the output is having the minimum error as possible. Okay, so the basically with regard to this system, that is how I think we are going to be focused on updating the filter coefficient. So when we discuss about these systems, we can consider like systems that are having special features. So this one is basically the block diagram of the adaptive filtering case. So we are going to consider some specific signals for this adaptive filtering case. uh, the 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 signals we are considering are basically signals that show WSS process. So in here we are going to consider XN, right? So I'm going to actually um, maybe write somewhere near this signal. So the XN that we are going to consider here is going to be something of a zero mean and WSS. So XN is a random process that that will generate random outputs. So this XN process is going to be assumed to have zero mean and also assumed to be WSS. So we are going to first analyze this system under these conditions. Okay, so first, in order for us to consider a simple case, we are going to consider with xn having zero mean and WSS properties. WSS means wide sense stationary properties. So we have discussed that wide sense stationary processes have equal statistics, all the at all the equal statistics during each time instance of the of a realization, right? So if you consider the statistics of average, if you consider average of the signal, then you can observe that average is constant without at every time instance. It doesn't matter which time instance you are considering, the average of the random process is going to be equal to the other average value that of another time instance. So the WSS process is a special process which has uh, statistics up to the second order uh, staying constant over all the time instances of the random process. So the mean value, the autocorrelation, cross correlation, those values are equal at each time instances of the random process. The random process might consist of multiple random realizations, right? So I think in the random processes class, we looked at how there could be multiple realizations of a certain random process. All these multiple realizations will have the different statistics. However, if it is a WSS process, then the whatever the mean value that you calculate at a certain time instance T1 over all the different realizations will be equal to some mu value, let's say. So the average value of the amplitude or some kind of a input signal x will say x will be mu. The average value that you observe at time t1 will be mu. So I will write it ex ext1 will be mu. So similarly for each other time instances also it's going to be like that. So x this t1 will be equal to ex t2 likewise. All these will be equal to something called mu, some constant value mu. At each time instance, if you take the average over all the different realizations of this function, of this random process, then you can say that they are equal to mu, right? If the process of xn is a WSS process. Similarly, we are going to consider a system where we have yn or other coefficients of the system, which are yn and en. Those things we will also consider, and we can say that the desired signal that we are considering is also a WSS process. So we are going to make those assumptions when we are working with this system initially. So dn also we are going to assume that it is a zero mean and WSS process. So uh, desired signal and xn signals, these are some things that we assume that we know about the system initially. Next, we are going to actually update the yn as we change the filter coefficient. So this yn is the output signal. And we consider that this filter is a M-tap filter having M coefficients. So we assume that we know the coefficients initially of this filter, M-tap filter. So initially we know that its coefficients are H1, H2, H3, H4. Likewise, we assume that we know that. So H2, H3, H4 up to HM, we assume that we know of the filter coefficient of the filter, which is coming from the impulse response of the system of the filter to a certain impulse. So these filter coefficients initially we know. So, as we assume that we know that, after that we can denote the output of this yn, or the yn signal we can denote as the convolution of the uh, input signal with the filter coefficients. So this one we can denote using hn convolution xn, and this one we can denote using a summation where we can say that the filter coefficients are multiplied with the delayed version of the input signal. This is m in here. So u n minus m. So these are the things related to the filter output. So this equation can be used to analyze the filter output, and also we can see that the input signal and the output desired signal are WSS processes. So these two signals xn and this signal and the desired signal are both WSS processes. So because of that, we say that xn and dn are jointly WSS. Those are the initial considerations or parameters of the filter. So after that, we can also mathematically denote these parameters using vectors. So the filter coefficients of this filter coefficients that we have in here, H1, H2, H3, H2 up to HM, we can denote using a vector. So we can denote that vector as H. So this is a H, which is a vector, and that can be denoted using its coefficients, where we denote it as H naught, H1, H2, likewise up to HM, M minus 1, because we are starting with H naught. The amount of coefficients will be total M, but the indexing will be uh, going up to M minus 1, or capital M minus 1 in here. Okay, so it's capital. After that, we can also denote these other vectors also. So in here, this filter coefficient, we denote generally using this column vector, or we denote this coefficients as this column vector up to H M minus 1. So we have the ability to show that as a column vector. And then when we do the calculations, we do considering that this filter coefficient vector is a column vector. After that, we can also do this next definition, where we define the input signal using the vector. So the input signal x, we took it as xn, and xn also can be denoted as x naught or xn minus 1 up to xn minus m plus 1. In here, this one also we consider as a transpose vector or a column vector. So x1, x2, x3. Likewise, it will go up to xn minus m plus 1. So all these things will be denoted using time indexes, the input signal. So we'll be basically using time indexes to like denote each time sample specifically. So the time sample of the the input signal samples will be denoted as a column vector. So that is basically done when we are adding the transports here. The transpose here. So we basically are dealing with column vectors. After that, we have this the definitions, right? Other definitions are also there that we can initially make regarding the input signal. So if we have this input signal, we can define that the input correlation matrix as Rx. Rx input correlation matrix Rx is equal to the expectation of the xn value, or the process xn with the transpose value of xn. So when we are taking this product like this, we are actually taking the product of a product which is given in here, which is we take the expectation of this column vector uh, with its transpose. If we are doing that, we are getting a matrix where we have vector elements from m by m matrix. We are getting a m by m matrix. So that I think we can do as we have done in the last sessions where we found the autocorrelation value of a input signal. So we can multiply this xn with its row vector. So in here xn value you can multiply with its row vector. So let's consider only an example in here in order to simplify the calculations. So we will consider n up to 3 or something, and then we define the x1, x2, x3. Then we take the multiplication with its transpose, which is x1, x2, x3. Then the entire thing we take, and we take the expectation of the entire thing. So we can multiply this, and then we can produce a like a 3 by 3 matrix. So this, because this multiplication is with 3 by 1 and 1 by 3 vectors. So there will be a 3 by 3 matrix in here. So the 3 by 3 matrix will have special properties, and that 3 by 3 matrix will have uh, like a positive definite matrix behavior. Any questions up to this point? Okay, so what you need to know is that this input signal xn multiplied by its transpose value x transpose n will result in a 3 by 3 or an m by m matrix. In here we only consider the sample, but if for a considerable like a general scenario, this is going to be an m by m matrix. Similarly, we can also consider some other metrics where you consider RUD, where you take the expectation of the this input signal xn, not, so I will take as RXD, where you are comparing the input signal with the desired signal. So I will take the multiplication product bit for the product between this input signal and the desired signal. So this will actually give the cross correlation between xn and dn. This will give me the autocorrelation of input signal. Autocorrelation of xn will be given from this expression, autocorrelation value. So those are the definitions that are required for this analysis, where we are going to find the optimal filter coefficient. So the goal is to find the optimal filter coefficients. So if we consider a scenario where the number of samples k is bigger than the number of filter coefficients m, we are going to consider the vectors um, of vectors we are going to consider. So um, So let's say we are going to consider like a data sample set which starts with n naught plus 1 up to n naught plus k minus 1. And in that case, we can derive the optimal filter coefficients for that case. We are going to consider this scenario, and we are going to consider uh, the data samples that we are going to consider are from time index, which is equal to some certain time index n naught, n naught plus 1, n naught plus 2, likewise up to uh, n naught plus k minus 1. So up to k times of data samples we are considering. Okay. So in here, since it's starting with 0, the total number of data samples we can observe is k, capital K. K is the total number of data samples of considering. And then we can define the different input signals, desired signal and error signals using these vectors. So if we consider that the uh, the input signal, we can denote the input signal using this. This is a vector. So we will denote the vector using a certain single symbol. So this is the vector u. U is equal to u n naught, then u n naught minus 1. Sorry, we will take this as plus 1. We consider that u n naught is the most uh, most recent one, most recent data sample that we observed. No, it is most most oldest data sample, then the data sample at n naught plus 1. Likewise, up to the point where n naught plus k minus 1, we take data samples that we denote as a vector in here, and that vector we denote as u. Then we can denote the other vectors with desired signal and then the error signal. So for desired signal, this is going to be a desired value at n naught, then desired value at n naught plus 1, likewise. Error signal also we denote as error at n naught, and then error at n naught plus 1, and then error at n naught plus k minus 1. Those are the error values and the desired signal values at the specific time indexes n naught up to n naught plus k minus 1. All these vectors we can denote as column vectors. So for denoting as column vectors, I'm going to add this transpose sign in here. Okay, so I hope you are familiar with the matrices, or else you are able to look at the lecture note that I shared in the LMS, which gives you the basics of the matrices and their definitions and how you can define, things like gradient, Hessian of a matrix, and also a certain function, right? So those things will be useful for you to understand this, concepts of vectors and then column vectors. So after that, we are now going to try to find, our goal is to minimize the error, right? So whatever we are going to do, we are trying to minimize the error in the output with respect to the desired value. So the main goal is to minimize the error. So the error we can define mathematically using this expression, where we denote that error is the difference between the desired signal and the output signal. Right, so output signal we can further define as the input signal uh, transpose into this filter coefficients. So input signal I will denote as x, and then filter coefficients as h. Right? So in here, sorry, I think I have to denote this input signal as X in here. So in here, the goal is to minimize the error and find the optimal, filter coefficients that allow that enable that. And so we have to minimize the error and we have to find the optimal filter coefficients that do that. So in order for us to minimize the error, we need to find uh, the optimal filter coefficients, and we have to find the mathematical equation that we can use to find the optimal filter coefficients. So in order for us to derive the mathematical equation, we need to denote this the error value using some kind of mathematical equation where we are able to then construct some optimization problem to minimize the error. So have you learned about optimization techniques in the previous sections or modules? Anyone? Any idea about optimization functions? Have you learned how you can do optimization?
No, ma'am, I wouldn't say so. We didn't have something like that.
All right, so thank you. So I think good to know. So I think in your um, maybe some degrees teach optimization during bachelor's. So optimization is a technique that we are going to find uh, you know some optimal parameters uh, uh, considering considering a certain application and some kind of a goal that we want to achieve. So in here, what we want to do is we want to minimize the error. And for that, we want to find the optimal filter coefficients. And that we can denote using a certain optimization problem. And by denoting that optimization problem, we can find the optimal filter coefficients by using some techniques that we know uh, and that we can use to solve this problem, optimization problem. So it's not a big deal actually. Optimization is something that just denotes a certain problem mathematically. Then after that, we have to find some methods to solve that optimization problem. And that method could be a certain statistical method that we have in mathematics. So in this section and in this part where we are trying to minimize the error, we can use this method we discussed about, which is the least mean square method. So least mean square method we will be discussing about. So that is what we are going to use to minimize the error. So before like minimizing the error, first we need to define the objective function, and that objective function that we are going to consider to minimize. So first I said that we are going to minimize the error, but we are not directly minimizing the error. We are considering some error squared value to minimize. The reason being that error value in here can be something positive and negative. So if the error value is negative at some point, we cannot really find the exact effect of that error. So we need to consider square value of the error. So by doing that, we can easily get the absolute value of the error, and then we can take the effect of that into consideration, and based on that, we try to find the filter coefficients. So I will talk about the optimization optimization problem next. So for optimization problem, I mean, the reason I wrote it was that we need to use optimization problem to minimize the error. But when we are implementing this, first step is to define a certain objective function that we are trying to minimize or maximize. We need to define a certain objective function, and also we have to define some constraints under which this optimization will be considered. So we have to define the constraints. So we have to define the objective function, then we have to define the constraints, then we have to define whether we are maximizing or minimizing. So whatever the operation that we want, we have to either minimize or maximize the objective function. So when we are considering in this situation, the optimization problem that we are trying to solve and find the answer is the optimization problem where we have objective function equal to a function which is like this. So minimizing the squared value of the error, so that, right, so we are able to find the optimal filter coefficients. So minimizing the mean squared error inside. So this is how it goes. So we will see. So in here, I will denote the filter coefficients in here. So in this is what we are trying to find. We are trying to find the filter coefficients that will minimize the error, the squared of the error. So this is the squared of the error, and this entire expression will give us the mean squared value, right? So the expectation value will give the mean value of the squared error. So we are trying to minimize the mean of the squared error such that the filter coefficients can be obtained once we do that. So the objective function that we are considering is this mean squared error objective function, or we call this as cost function. Objective function over the cost function, and that one we did define in here as the mean squared error function. So mean squared error function, which we again we denote as expectation of the error value squared, right? Error value we take the square value of that, and we take the expectation value to get the average value of error at that point, right? So this objective function will be used, and then we will try to minimize that with and then we will try to find the filter coefficients, optimal filter coefficients when the when that minimization occurs. So when we are doing this, optimization, we have to make sure that there's actually a minimum point to this function. Otherwise, we cannot find the minimum value. So in order to do that, we need to do some tests. We need to do some set tests and find out whether this function actually has a minimum or not. So for that, we are going to use something called finding the gradient, then finding the Hessian, those things. Any questions up to this point? So those are mostly some things that are very mathematical and also like related to matrices, and also like finding the gradient means like finding the differentiation of a function. So those are related to, I think, optimization, and also they are related to machine learning aspects as well. Like when you're learning related something related to machine learning, also you will go through these sections where you will be learning about the gradient descent, then stochastic gradient descent algorithm, and least mean square method, likewise. So mean square, the error method, those things. So those are some things that you are learning with when you are learning about, for example, machine learning, where you will be learning about the data, and how we can compare the current data with another set of data. Okay, so something similar we are going to do in here as well. So that is why we are using the same statistics in here as well. So in here, what we are trying to compare is that we are having a certain filter output. We are trying to compare the filter output with our original expected filter output. We have an expected output, but if we don't have it, we don't get it. We are now going to fix the filter and adapt the filter such that the filter gives the expected output as we require or as we desire. So these kind of applications are like these kind of filters are used in applications where you are if where you want to reduce the noise, for example, of audio signal. Suppose you know the audio signal that you want from a, like, after you filter, you are getting certain output, but that output, that it should be similar to certain audio signal. If you know that, then you can compare the expected output with the one that you obtain. So these kind of filters that we're talking about are basically used for scenarios that you know the exact output, and also the desired output. Then you can compare those two things. When we go and find this optimal values of filter coefficient, let's say I denote the optimal filter coefficients in this vector. Let's say this is a vector that denotes the optimal filter coefficients. So we are going to now compute that optimal filter coefficients. So that one we can consider. So in cases where we don't know exactly the filter, I mean this function, error function, right? So in the last session, I showed you the case where we know the error function, right? when we know the error function exactly, we can find we can find the values of the minimum point where values of the filter coefficients. So in here you can see that we have drawn a certain function with respect to the filter coefficient, and in here we can use this if we know the error function in a certain manner. Like if we know the error function using probability and any other method, then of course we can use this function to obtain the gradient, and then we can find the using the gradient we can find the filter coefficient. So not all the time we know this function. So error function we might not know in some cases. In such kind of cases, we have to go for other methods of deriving this optimal filter coefficients, which are mathematical. So we might not be having an idea about this function, but we will use mathematics to find the optimal value of the filter coefficients with the other, using methods. So in here we will be using that kind of a procedure to find the optimal filter coefficient. So optimal filter coefficients in here we were going to find by like taking first the we are going to solve the problem in the different steps. So I'm going to say step 1. So we are going to construct the cost function. So the cost function is this one where we have this expectation of en squared. That one we can expand and we can get it into a state where we have it in terms of what we already know, and like we can write this expression with terms that we already know, so variables and parameters that we already know. So therefore then we can find the value of this objective function. We are going to derive this objective function and kind of expand it, that we are going to like simplify it further into expression that we know of. So this entire expression I can also denote as JH, where we are trying to find the optimal values of the filter coefficients. So this expression I'm going to denote as JH, which is objective function. So objective function I will get, and I will denote as JH, and then that is equal to expectation of the e- error squared, and the error value I can denote as uh, the difference between the desired signal and the output signal, right? So there's a square in here. The yn value we defined earlier as this x transpose n into h. So based on the vectors, actually I have taken that, right? So x transpose into h. So in this one, I have x transpose n into h. Then I take the square So this I can denote again using by uh, like dividing this into two factors. I can write this as dn minus x transpose n h. Then this entire thing I can take the transpose. Then I can take dn, the same thing, dn minus x transpose n into h. Right? So this is something that I did now to get these two factors separated out. And if uh, you consider like why I wrote like this, so if you like, I will take an example to explain this. So if you have a certain vector, let's say if you have a certain vector e something e1, e2, e3, there are three values. Let's say it is a column vector, and then I'm going to multiply it with its transpose, which is E1, E2, and E3. So the value that I'm getting finally, once I multiply E and ET, is basically if I'm going to multiply uh, E and ET, of course, I'm going to get a 3 by 3 matrix. If I'm going to multiply the uh, vectors in the order where I multiply this transpose, ET transpose, with the E, which is E1, E2, E3. With E1, E2, E3, I will be able to see that I get this E1 squared plus E2 squared plus E3 squared, right? So this will enable me to get the square term separately by taking this product where you multiply the that vector with vectors transpose with its normal value. Same thing has been done in here. And so this will be equal to the case where I take the square of each of the values of the whatever the vector, and then I take the sum. It's something like this. So if I go up here, in here also we want to take each and every individual square value of the value of this signal. Therefore, we want to multiply the transpose value of that vector with its normal value, vector value. So if you do that, you will be able to get the square terms of each of these, and then you will be having the sum of it, and uh, basically you will be taking the average of it. So in here you are anyway you want to take the sum, and then you want to take the average of that. So if I take the multiplications, I will be separating the square terms first that I'm getting with the same term. So I will be multiplying dn with its dn transpose, which will give me the squared value of dn. Then I will multiply these two terms. So I will be multiplying this is h transpose. So you also can try to solve this meal the meantime. Okay, so in here I have uh, first term. I think it's not a problem. In here I have taken the expectation of dn squared, which is like since dn is like a zero mean process, mu is zero. Because of that, expectation of this dn squared actually equals the variance of this dn signal. The variance of dn will be given in here as sigma d. So sigma d squared is the variance of this dn signal. So that part, I think it's clear. After that, when I multiply with the uh, you know this second term with the other second term, then I can get this one, where I can take the h h out, because h is something that we know of the system. So filter coefficients that initially we have in the filter, we know. So we are taking that out. So from both sides of the equations, terms, I'm going to take h transpose and h out of this expression. Then I'm going to take only the expectation of the xn and x transpose n, which where you have the x signal which is a random signal. So only that signal will have that certain expectation operation applied on, because it is the one that has the you know some kind of a probability of probability density function associated with it. The filter coefficients are constant, so we can take them out. So once I do like that, uh, this expectation operation that I apply in here will be applied to this xn into x transpose n term, which denotes the autocorrelation value of the input signal xn. So that autocorrelation of the input signal I denote using this Rx, capital Rx. So, so we have these two terms, variance of the desired signal and the autocorrelation of the input signal from the first two terms of this product. After that, when we consider the other two terms that we have in here, so in here, in these two terms, in the third and fourth terms, we are having combination of the filter coefficients and the transpose of the desired signal and the input signal. If we consider of taking out the filter coefficients, we can take the filter coefficients out by taking the transpose of this term, entire term again, and then we can invert the position of these vectors. We can take the filter coefficient, this term to the front by taking the transpose of this entire expression. Once I do like that, then I can get the, I take the transpose of this expression, and then I can take the H transpose into the front. So in here I have dtn, xn, xtn, and h. So once I take the transpose, I will be able to get H transpose, then dn and xn. So this is the expression that I will be resulting with. And if I take the expectation of that, I will be able to take the HT outside, and I will be able to keep the rest of the terms inside the expectation, which is dn and xn. Then afterwards, I can compute this last expression. There actually I have this HT term in the middle of the expression. I can take it as a constant, and I can take it out directly. I can take it out, and I can denote it outside the expectation operation. I can take this dn and xn into one term, and then I can use the summation, and then I can consider that this is 2 into ht into e and dn and xn. So like that, we can simplify this expression. So uh, by doing so, we can actually, in here I had to put 2. We can get this expression where this rdx or simple rdx is used to denote the cross correlation between the signal dn and xn. So this rdx is used to denote the cross correlation between the dx and dn and xn. So cross correlation I denote using this simple rdx. So this expression we can get as the error function. So this is the function that we have to minimize. Now we have this expression in terms of the filter coefficients. So now we have to minimize this error value with respect to the filter coefficient values. So this is the goal. So minimize the error values. So when we want to find the minimum error value, as I said, we have to find the gradient. So the second step in this calculation will be finding the gradient of the cost function with respect to the filter coefficient. So the first step 1 was constructing the cost function. So second step will be finding the gradient of the cost function with respect to the filter coefficient. So the gradient value we can find by taking the derivative of this function with respect to the filter coefficient. The derivative of this function we have to find. So the derivative of this en, whatever the function, which we can denote like this. I'm going to take the derivative of this function with respect to h. In here, I can see directly that this sigma squared d is a constant value for the desired signal and does not depend on the h value or the filter coefficient value. So once I take the derivative of that term, it's going to be 0. So in here, I'm not going to go into the derivation process like in an explanative way. You when we are deriving the differentiation of the second term with respect to the h, in here there's a kind of complex term, and in here you have to use some product differentiation. So when you are differentiating a product, then you have to divide that term into two parts. So differentiation of product can be used to solve this. And finally, you will be getting this expression where you will have capital Rx plus Rx transpose into H as the answer. So this one you can obtain by taking the derivative by considering the product between two terms. So that I think you can consider like finding the derivative of this expression with respect to H, where you have first HT, you take the derivative of that, multiply that with the Rx H plus, then you take the H transpose, and then you take the derivative of the second term with respect to H. By solving this, you will be able to find that this actually equals this one. So also this derivative of H transpose with respect to H will give you 1. So because of that, this term will be 1. So that will result to having Rxh plus this term having uh, like H transpose and Rx. So this will result in H transpose Rx. Further, if I take the transpose on both sides or take the transpose, then I will be having Rx transpose into H. By doing so, I can finally, I mean, I can get the final answer as Rx transpose H for this, and for this term, I will get Rxh. So by the addition of this, I will be able to write that the final value of this derivation differentiation will be Rx plus Rx transpose into H. And then after I can take the differentiation, this third part where I take the differentiation with respect to H, and in here it's going to be 1, or the differentiation of H transpose with the H is going to be 1, and then I'm going to be left with 2R dx. So this is the final output that will be there for this differentiation. Also, I mean, okay, so in here as Rx is going to be equal to Rx transpose. So for a WSS process where the xn is a WSS process, Rx equals Rx transpose. The matrices that you are getting is symmetric. So a symmetric autocorrelation matrix is there for the input signal. In that case, you can write that this is equal to R2 into Rx, and then multiply that with H. So with that, this expression will have 2 as a factor in both sides, in all the terms. So that also we can remove once we want to find the optimal value of the filter coefficient. So going further, we can write that this is equal to 2 into Rx. So X is a subscription in here. So Rx H minus R dx. This is what we will get. So if you want to find the optimal coefficient, you want to find the place where this is equal to 0. right? So in order for us to get the optimal coefficients, we need to find then the find the value of h which makes that expression 0. The value that makes that 0 is the value that makes the Rx h equals Rdx. Right, so inside these brackets I have this expression, and inside this, so this one should be equal to 0. So if that is the case, if I want to find the h, I need to take the inverse of this matrix on both sides, assuming that the inverse of this Rx is available. That means Rx should be invertible. Assuming that Rx is an invertible matrix, I take the inverse of Rx on both sides, and by doing so, I can make the filter coefficient so value h the subject of this equation. So by doing this, I can find the optimal value of h. I can, if I know this value and if I know this value, I can find the value of optimal value of h. So for me to know the value of this autocorrelation value, I need to know the input signal, right? If you know the input signal, you can find the autocorrelation matrix in here. Autocorrelation matrix is something that you want to know in here. If you know the autocorrelation value, then you can find that. This one means the cross correlation value of this desired signal dn, cross correlation of dn and xn. If you know these values, you can find the cross correlation value. By doing all this, I mean, if you know these values, then you can find the optimal value of the coefficients, right? Optimal coefficients that will minimize the error. So that is regarding finding the optimal values, right? Sometimes, however, you have to go further than this as well, where you want to find whether actually you have this, whether you have a minimum point value which will minimize the error. In order to do that, you will have to find the place where you have the Hessian of this matrix or of this function. Hessian value should be positive. We denote the Hessian as HW or H. Uh, we just denote it as H, and inside H. H means Hessian. Hessian means they are taking the differentiation of the cost function 2 times. We are taking the differentiation of the cost function 2 times with respect to H. The cost function that we initially chose was this error function, right? So error, the expectation of the error. This one. this one we already know. We already know this gradient value which we calculated in here. This is the gradient value we calculated, GH. So we have to take the differentiation of the GH. So differentiation of GH means that I need to take the differentiation of this one, RxH minus RDX. So, so when I take this is going to be not related to H. So because of that differentiation of this one, it's going to be 0. Only remaining one is Rx. So Rx is the Hessian of this matrix. Okay, so there was a term 2 also at the output. At the output earlier, I think there was a 2 also, but I'm going to disregard that. So the Hessian is going to be approximately defined using this Rx matrix. So if that is the case, if Rx is something positive definite, then H or the Hessian is going to be also positive. So I go up again. I can write this 2 also just in case, because I have to take the differentiation of this gradient with respect to the H. So the entire term I need to consider in that sense. So I need to have this 2 also in here. So I will have 2 Rx in here. So in order to get the full effect of value of a Hessian, I need even the coefficients that are related to this expression, and which is the gradient. So in here, if Rx is positive definite, then the Hessian is going to be positive. Hessian value is going to be positive. So Rx being positive definite means that all the eigenvalues of this matrix are going to be positive. Positive definite means that definitely all the eigenvalues are positive. If some matrix is positive semi-definite, that means that some of the values of eigens could be 0, but others are positive. So either 0 or positive, the eigenvalues can be if it is a positive semi-definite matrix. But if it is a positive definite matrix, that means all the eigenvalues of that matrix is going to be above 0. That means they are positive. So if that is the case, that Hessian is going to be positive. If the Hessian is going to be positive, then we know for sure that cost function is if Hessian is going to be positive, then the cost function has a minimum. That means in our case, our error is going to have a minimum. So the error function will have a minimum. So therefore, whatever we are doing here can be successful, and we can find the minimum point where the error occurs. So from these steps, what we have gathered was that one thing is that the function that we have considered as a cost function is a convex function. Convex means that it is going to it is having a minimum value, right? The cost function, right, considered as a minimum value. Okay, so the cost function we considered was this, right, this one. This is the cost function. then that Rx is invertible. Mainly because it is I mean, it is actually invertible, like a square matrix, and also is a positive definite matrix. So Rx, so it's mainly because uh, it's a positive definite matrix, mainly because this Xn signal is a WSS process. It is generated as a WSS process. So for WSS or wide sense stationary processes, the metrics that we are generating or we are having is going to be always something positive definite or positive semi-definite. So because of that, all the eigenvalues are going to be positive in that. So in for WSS process, it's defined that the matrix that you are having is a positive definite matrix. All the eigenvalues of a WSS process is going to be positive, and therefore the input correlation matrix is going to be a positive definite matrix, which means that it's having an inverse, and it is also symmetric, and it is square likewise. And also this whatever the optimal filter coefficients that you are having obtaining will be the optimal values of the optimal values that could minimize the error. So this is known as the global coefficient. Global coefficient means that for a certain function, there could be sub minimum point or sub optimal points. So what I say is that the in here in this if you have a certain objective function with an error varying like this, let's say error value is going to change. Let's say it's going to change in this manner. So if there are points like this, A, then there's a point B, and there's a point C. So out of these A, B, C points, what is the global minimum point? Do you know, can you just say like, what is the global minimum point? So in cases where you have this kind of a function, yes, no, the global minimum point is going to be C, right? So minimum means like the point which has the minimum error value. Error value minimum going to be the point C in here. Is it clear? So the value of error will be minimum in this point under a certain coefficient. So that minimum point we have to find. So in cases we have such this kind of multiple minimum points, in order to find the global minimum point, we have to follow the steps that we just discussed, where you first find the gradient, then you find the Hessian, then you find whether actually the Hessian is positive. That is the case, you can find the minimum point of the error function. Otherwise, sometimes you will find a minimum point, but it might not be the global minimum, right? So if you just use the gradient function only to find the minimum, right? So what I'm saying is that if you take we have done this step by step process. in here, if I find the gradient and I stop from here, and I just find some, if I just find some coefficients using this gradient function, and I find the coefficients that are related to this gradient function being equal to 0, then in that case that sometimes I will find a filter coefficient values or values of h that relates to a certain minimum point in the graph. But I might not be able to be ensure that this actually relates to the minimum point in the graph. You know, like this graph can have filter coefficient values, and that will relate to certain points in the graph. So this point A will correspond to certain filter coefficient values. And I might be able to find gradient equals 0 in here because the slope has a minimum in here. I will be able to find a gradient becoming 0 point in here. But in that case, although I find the minimum point and find the h values, this might not be the optimal, filter values. Then there's actually another minimum point in another place, so in another h value. So I need to find the other h value, which is actually the global filter coefficient values, which gives us the minimum error values anytime. So in order for me to find this global point, I need to take the third step where I find the Hessian value, and I make sure that there's actually the minimum point in this function, and that for a certain specific filter coefficients, the then I have been able to find the minimum point in the function. So if you read about this Hessian, you will get to know about that further, about the global minimum of a function. So with that, I think you can find the global minimum points of a function, and the global minimum error can be found. So the filter coefficients that give the global minimum error can be found using these steps. Once you have done that, you will be able to implement that coefficients into the filter, and then from that we can get uh, maybe reduced error, right? So you can update the filter coefficients of filter coefficients, and then you can get a reduced error from the filter. Optimal H naught values that we have obtained will be we have obtained them in this place where this H optimum is equal to Rx inverse and simple RTX. So this one. So this one I can substitute in the error function, and I can find the minimum error. This one I can substitute in the error function that that constitute of the this expression that we got earlier. This is the optimal error function. Oh, sorry, this is the error function, and to this we can substitute the optimal filter coefficients instead of h in here. Then we can find the optimal error or the minimum error that we can obtain. So minimum error we can find by substituting the optimal error coefficients into this expression. To this, I will substitute these coefficients. So in here, I get Rx inverse. Rx inverse. So you can solve up to this point. So what I did was substituting this h naught into this h terms in this expression, wherever you get them. And then once I take the transpose, I can turn the terms into the other way around. So if I take the transpose, I have to take this term into the front, and then I write in the opposite direction. Afterwards, like in here, I cancel these two terms, which are Rx into Rx inverse. Then I'm left with Rdx and these other terms. And for the final term, I have again substitute with the h, this with this term. And there also I have this transpose term. So I add the transpose and I invert the two expressions. And then once I add these two, I can see that they are most similar because every term is similar in both these two terms. So I can add them. And what I'm left with is this Rdx transpose, and then Rx transpose is also remaining, but I put as Rx inverse because Rx transpose in inverse transpose is also equal to Rx transpose because this is a symmetric matrix. Rx is a symmetric matrix. So because of that, even though you take the transpose, it will be equal to the same matrix you get when you have the normal inverse operation on. So this will be equal to each other. So I will be able to therefore have this expression. So I'm having this final expression where you have this error, minimum error of minimum error that you can obtain is this given by this. So this is the minimum error. Minimum error that is possible is given by this expression. So that is regarding how you get the minimum error. So minimum error you get like in this position in the graph. So in here the cost function is error squared. So expectation of error squared we will take as the cost function. We have been taking as the cost function. So in that case that the error will have a minimum point in this place, and this kind of a place is what we are trying to find. So in here the optimal coefficients you get will be the ones that we are going to feed into the filter. So optimal values we can find using this method. So I think that's about it for finding the optimal error value and then finding the optimal coefficient values. So I will discuss some sample questions regarding this concept, mostly in the next class. So in today's class, we have discussed about these adaptive filters. So in today's class, we have discussed about these adaptive filters, and adaptive filters we have discussed about how we can model the error value of the uh, filter, and then we can find the optimal coefficients that will minimize the error. So adaptive filters are used in many practical applications where you want to, right, they are used in practical applications where you will be doing noise cancellation, especially in audio signal processing, where you are processing the audio signals. You can search about the applications of adaptive filters on your own. So one application will be audio processing, and then even in wireless communication, you will be using equalization of the received signal to remove any noise and interference from the received signal. So interference and noise will be cancelled, and also effect of the remove any effect from the channel, right? Remove channel effects. So equalization will be done to remove channel effects and obtain the desired signal. For such kind of applications, we can use these adaptive filters. Also, signal enhancement for such kind of applications where we want to improve the amplitude of the desired signal, we are using adaptive filters. And then also we can use these adaptive filters for system identification. So in here, what I mean by that is that if you want to find an impulse response or some response, properties, features of a certain system, we can find the features by using adaptive filter. So such kind of practical applications are there in for these filters. So adaptive filters are used to adapt and change the filter coefficients based on the requirement of the application uh, that we are considering. So we are going to change the coefficients based on the specific application. So we are going to use for different applications such as noise cancellation applications, so related fields such as like telecommunications, even biomedical signal processing, audio processing, all those things will require noise cancellation. And then also you will be using equalization. For equalization process, you will be using adaptive filters, and those things will be used in, especially wireless communication. You will be removing the channel effects. So the effects that were added by the channel through which the signal is transmitted. So in that case, like, you are going to remove the channel effects through these equalization methods. Then signal enhancement, like, you're going to enhance the desired signal further, such that you can identify that signal with much efficiency and more clarity. After that, system identification is also possible with the adaptive filter, where you don't know the system transfer function, and you can find the transfer function use this adaptive filter. So those are some of the applications of the adaptive filters. So those are the things that we can discuss about the adaptive filters. So in today's session, we have discussed about this, like how we can model the adaptive filters, filter coefficient, right? Modeling of filter coefficients. We have modeling the optimal filter coefficients. We have discussed using the least mean square method. We have discussed. Then applications of filters, adaptive filters. So these are the things that we basically discussed. After that, in next classes, we will be discussing about something which is related to the stochastic models. So models such as, we are going to talk about stochastic models such as average. We call this ARMA, which is like autoregressive moving average model. So there are some models that we can use to um, find uh, different coefficients of a random signal, and we can estimate the coefficients of the random signal using this model. We will discuss about that in the upcoming classes, which is also something that we need to cover. So I will be discussing about that in the next class. So with that, I would like to wind up today's session. Any questions you have, I would like to answer right now.